That's your virtual classroom. Now, especially if you guys weren't here. If you weren't here for this part, the chi-square works a little bit differently. We don't have a test in your calculator for this. And it works off of two formulas. The main part of that formula is these two little codes on the bottom. The chi-square left, the chi-square right. X2L, X2R. And to find those, we use table 6. Table 6 has across the top, it's symmetric down the middle. So if you drew a line down the middle, you'd see 0.10, 0.90, 0.95, 0.05. You get a pair each time. So to do this, we still say, just like you would do inverse norm, as if you're doing inverse norm, you're still saying 1 minus 0.99 divided by 2. Only there is no inverse norm. So this becomes 0.005. Now, subtract this from 1, 0.995. So in your papers, table 6, you're going to see here and here. Doesn't matter which one is which yet. You'll be able to determine it. Come down to your degrees of freedom, which is 1 less than this, and pull out these two numbers. They're always positive. Your chi-square always goes from 0 to infinity. It is the only one that references area to the right. So I don't want you to get confused. So we always solve it the same way, but it's just a backwards approach, but that's okay. The smaller number, the less number, the least number is the L, the left. The larger number is the R. That's key to this whole thing. So if you weren't here or you're not getting a good grasp on this, that's the most important part. Whatever confidence interval we give you, you subtract it as if you were doing this with your inverse norm, but you're not. So you're getting 0.01 subtracted from 1, 0.99. So in your papers, you're looking up 0.99, and you're coming across to 0.01. Degrees of freedom, 25, and you're pulling off these two numbers. It's like this, from 0 to infinity. So the smaller number is the left, the larger number is the right. It's kind of like if you did it backwards, you're going to see it when you do your equation, because we build your interval. It's an inequality. We build your interval as an inequality. If your inequality is backwards, all you have to do is swap them around. The beauty of this formula is the numerators are the same. So the key to this is your denominator. So again, 1 minus 0.80 divided by 2, and 0.1 and 0.90. This actually is right in the center of your table 6. So we pull up these two numbers. Can everybody do this? Okay, and those of you that weren't here, follow along with me. Now, here's the formula. And I will give you this formula. Here's the piece you just found. X2L, X2R. Your word problem, or lack of words here, will give you the rest of the information. Notice the two numerators are exactly the same. And n minus 1 is what? Degrees of freedom. So degrees of freedom go right in here, 29. This is the tricky part, this S squared. S squared is a sample variance. S is a sample standard deviation. So notice in this one, they gave us the S squared. So I just take S squared out of my formula, and I plug in 11.56. I have the variance. We're doing this interval for a population variance, because we don't know what the population variance is. But so we're setting up your confidence interval for a population variance based on our sample. So again, with this guy, we do this. We find that 0.025. So sorry, 0.025, 0.975. We pull out these numbers. Notice the right one goes on the left side because you want to divide by a larger number to get the smaller number on the left side so that it goes with your inequality. If these two numbers were reversed, all you gotta do is swap them. Once you find this is your confidence interval for variance, you take the square root of everything. This is your confidence interval for standard deviation, population standard deviation. So technically, I'm going to be 95% confident that my population standard deviation will fall between these two numbers. Variance and standard deviations are usually small in this group. The key is, which one are they giving me? If they give me the S2, I replace the S2. If they give me the S, I have to put the S in and square it. And generally go 3 decimals on this. So these numbers will be close and they will be small. You probably can tell by the L1 that you put in. The numbers are close. Questions? Especially for anybody that wasn't here?
What's the difference between putting the square root and not?
We get 2. The one with the alpha square root is the sigma squared. That's our confidence interval for our variance, our population variance. When we calculate variance, then we take the square root and we get the standard deviation. Same, and in your calculator, sometimes you work backwards. Sometimes, you know, when you do an L1, you get an SX. That's your standard deviation. You need your variance. Remember how you go to that little table and then square your standard deviation? That gives you your variance. So one is just the square root of the other, or the square of the other, so whichever way.
You'll ask for them differently.
I will. So when you do this, there's no more calculations up here. We already did this. All you have to do is take the square root of everything. Just put it in your calculator, square root, and there's your confidence interval for standard deviation. That's the nice part of it. The formula looks horrible, but if you break it down, the 2 most important values are these guys right here. From your table, that's from table 6. And -1 is your degrees of freedom. You just found that to use your table. And determining if I have a standard deviation or I have a variance. Okay? This one, now, look how close those numbers are. Look how little they vary. That's why we do a variance on this. They're very, very close numbers. There's not a lot of leeway here. So, when you put this in your calculator, this is a sample of whatever it told us this was. You can only find a sample standard deviation. That's your SX, not your population. You are making an inference about your population. This is the inference you're making. You're using your sample to make an inference about the population variance and then the population standard deviation. So in your calculator, you're going to put this and you're going to find your SX. Look how small that is. They vary by very little. So 90%, we're going to do the 1 minus 90 divided by 2. Look up these numbers with your degrees of freedom. And these are your bottom numbers. Your degrees of freedom was 14. You found your standard deviation. And you just plop it into your formula. That's it. Take the square root of everybody, standard deviation. So we can be 90% confident that the variance for this sample of whatever this sample happens to be will fall between those 2 numbers. Look at how small they are. Yes?
How many decimals do you want?
Well, at least to a significant digit. If you just gave it to me here, I'd be happy there. It's at least to a significant digit. Remember in your calculator when you see this doesn't mean that this is 6.09. This means e to the negative 4. Move that decimal 4 places. This is a scientific notation number. Move that decimal 4 places to the left. It's got to be a very small number because they vary so little. Your standard deviation is small. So at least to a 3 decimals, but at least to a significant digit. And as long as your rounding is fine, I don't get hung up on the decimals. Good? Everybody has this. All of you guys that were in here too? Okay. Now they just put the squares. A magazine, blah, blah, blah. They selected 10 randomly selected compact digital cameras. Your N is 10, your degrees, sorry, your N is 11, your degrees of freedom is 10. They have a sample standard deviation, there's the S, and they have an 80% confidence interval. So subtract from 100 divided by 2. Look up these numbers. This is your X2R. This is your X2L. How did I know which is which?
The bigger numbers are.
Good. The bigger number's on the right. The lower number's on the left. L, lower, least. Plug these in, and now you have to notice you have to square this because they gave you the standard deviation. So notice you're just replacing the S, right? So don't you have to still square it? You don't have an S squared, you have an S. Find your confidence interval, take the square root, find your standard deviation. And again, you're making your inference for your population variance and standard deviation based on your sample information. Good? Okay. This is the last one. This is the last one. Again, you're testing 19 water quality things from a stream. You want to be 95% confident. Subtract it from 1 divided by 2. Find your L1, your L2. Your R1, your L, your X2R, your X2L. Find your, they gave you your standard deviation for your sample. So you have to square it and get your confidence intervals. Now again, if any time that your confidence interval is backwards, just reverse it. Just reverse it. If you messed up these guys, and you put the smaller one there and the larger one there, it's going to say this. And can that be according to an inequality? No. So just reverse these. The information is exactly the same except for the denominator. So that's what made it different. Just reverse it. Don't leave it to me backwards. And don't switch the inequality signs. The inequality signs go less than, less than. Questions at all? It's a pretty easy chapter, right? It looked bad when we first looked at it. But really, it's not so bad. Okay, so I'm going to give you... Well, I'll give you time today to do the review. Everybody wrote those down, right? All right. Today to do the review, and then tomorrow we'll go over it and test on Thursday. Sound good? That wraps up the rest of the confidence intervals. Remember, guys, E to your confidence intervals